Okay, here's one of everybody's favorite problem. Number 12, use the difference quotient. And the difference quotient is f of x plus h minus f of x over h. I will give you the difference quotient. Now, how you use it, that's entirely up to you to do it right. But the first thing you should do is calculate the f of x plus h. Okay, what does that mean to do? That means everywhere there's an x over here, you plug in x plus h. Okay, that is f of x plus h, and I'm going to do that in one color. So we're going to have 2 times x plus h squared minus 3 times x plus h plus 2. That all by itself, that is f of x plus h. And then your formula has a minus in it, and then you're supposed to subtract f of x. So always put parentheses around the f of x, and all you're doing is rewriting 2x squared minus 3x plus 2. And then that's all divided by, so this is all over h. Now you really don't substitute anything in for h, okay? So the minus is just part of the formula, the h is just part of the formula. The f of x plus h is where all your work is, and you plug in x plus h for every x. And then you minus the original function over here, okay? So that's your first step. You show me that you can do that step, that's worth some partial credit anyway. A lot of people struggle with the very first step, just getting it set up right. But that's something you should be able to do, especially after you do it a couple of times. Now the simplifying part, here's what we got to do. We've got to simplify this x plus h squared part. Now to do that, you need to multiply x plus h times x plus h. You may want to do it off to the side somewhere, like I'm doing in the top right corner here, or you may want to do it in your problem. I'm going to do it to the side because I've got space issues here. So x times x is x squared. You know, we're foiling this out. X times h is xh. H times x is another xh, because hx is the same thing as xh. It's called the commutative property of multiplication. H times h is h squared. You add these two terms together. Remember, there's a secret 1 in front of each one of those. And so when I add those together, that's x squared plus 2xh plus h squared. So I'm going to substitute that in for our aqua part here. So that's 2 times, parentheses still required, x squared plus 2xh plus h squared minus, okay, now I can go ahead and distribute this negative 3 inside, so that's minus 3x minus 3h plus 2, just recopying that, and then distribute this negative inside each of these terms. So that's going to make that a negative 2x squared, a plus 3x, and a minus 2, all divided by h. Now distribute the 2 inside. That gives me 2x squared plus 4xh plus h, I left a 2 off, plus 2h squared. What I do there, I distributed that 2 inside each of those 3 terms. Minus 3x minus 3h plus 2 minus 2x squared plus 3x minus 2. Now before this stage, you might have noticed some things canceled. And had you canceled them at that point, that's okay. I went ahead and just multiplied everything out before I even considered anything canceling. But here's what should happen at this point. Any term that doesn't have an h as a factor should cancel out. So look, this 2x squared cancels with this minus 2x squared down here. That has an h in it, that has an h in it. Minus 3x cancels with this plus 3x down here. And this plus 2 cancels with this minus 2 right here. So when I simplify further, that's going to give me 4xh plus 2h squared minus 3h, all divided by h. Now what's going to happen is this h can factor into each of these 3 things, or you could factor it out front. So h comes out, that leaves 4x plus 2h minus 3 divided by h. My h's cancel. Final answer, 4x plus 2h minus 3. Okay, so make sure you notice the tricks there. You're going to have to FOIL out x plus h squared if you got a square in your problem. You're going to have to distribute a lot. Any term that doesn't have an h as a factor should cancel out. Finally, this last step where you factor out an h and cancel with h in the denominator, that should happen every single time. All right, next problem. We're supposed to, can't read. Okay, we're supposed to evaluate the piecewise function. Part A, we're supposed to find f of 3, f of 1, and f of 0. It's like it's 3 separate problems. And then we're supposed to graph this thing. So first, let's find our 3 values. So f of 3. Now here's what I want you to know about piecewise functions. And you should already know this because you're at the review stage, not at the learning stage. But these guys over here are directions. This is telling you which equation you're supposed to use depending on your x value. Okay? So, if x is less than 1, you're supposed to use x. If x is greater than or equal to 1, you're supposed to use the equation negative x plus 2. So it's like it's 2 separate equations. Okay, so for f of 3, our x is greater than or equal to 1. So these are directions over here. So I'm only supposed to use the second equation. So I'm plugging it into the second equation. That's going to be negative. I'm going to remove the x, replace it with 3 plus 2. Of course, negative 3 plus 2 is negative 1. So f of 3 is negative 1. And now I'm going to reevaluate. Okay? So now I'm finding f of 1. Again, this is saying x is 1. What is my y value? So if x is 1, which one do I use? Do I use the top one? Well, no, because 1 is not less than 1. Do I use the bottom one? Is 1 greater than or equal to 1? It is. So I use the bottom equation again, and I plug 1 in for the x. So negative 1 plus 2, and we know negative 1 plus 2 is 1. And then for our third problem, f of 0. F of 0, we're supposed to use, which one? Is 0 less than 1? Yes, it is. 0 is definitely not greater than or equal to 1. So this time I'm supposed to use my top equation. So I plug 0 into that function and I just get 0. So my answer is 0. So that answers the first question, A and B and C. So f of 3 is negative 1, f of 1 is 1, and f of 0 is 0. Now I want to graph, all right? Now when you graph these, here's what the best way to do it. You do 2 separate t-tables. If you have 2 separate pieces to your equation. So the first one, you pick out x's, and you have y equals x. That represents the top part of your piecewise function. For the second one, you have x's. We're going to pick those out. And then y equals negative x plus 2, which is the bottom part of your piecewise. All right, so that's the way you get started. Now, for the top equation, notice it says I can only plug in x's less than 1. So what do you want to plug in? Maybe negative 2, negative 1, 0. All those numbers are less than 1. Now, here's the weird thing. I am also going to plug in 1 because I need to know what the graph goes up to but doesn't touch. So this open circle over here reminds me that when I graph that point, it's going to be an open circle that I'm graphing. Let's go ahead and get that over with before we move on to the second part. So if I plug negative 2 into x right here, that's just going to give me negative 2. Negative 1 plugged into x is negative 1, 0 plugged into x is 0, and 1 plugged into x is 1. So when I plot these points, and I'm going to do this in a different color, let's graph this part in red, okay? So negative 2, negative 2, negative 1, negative 1, 0, 0, and then there's an open circle at 1, 1, because the graph goes up to that point but doesn't go any further. So normally, this line would extend forever in both directions, but it can only extend to the left forever, because at the right, at the point 1, 1, the graph just stops. And it's an open circle. All right, now let's graph the next piece. So again, we're going to pick out x's, and we're going to plug it into y equals negative x plus 2. Now, what am I allowed to plug into the second piece? Well, it says x greater than or equal to 1. So I can plug 1 into the second piece, but remember, I got to fill my circle in. And anything bigger than 1, like 2 or 3, And I take 1 and I plug it into my x value. So that's going to be negative 1 plus 2, which gives me 1. And then I plug in 2, be negative 2 plus 2, which gives me 0. And I plug in 3, which will be negative 3 plus 2 gives me negative 1. So I'm going to plot the point 1, 1. Now look, check this out. This is an unusual case, but it happens. That open circle gets filled in by the other graph. And then we have 2, 0, which is here, and then 3, 1. How about 3, negative 1? I can't read my writing. 3, negative 1, which is here. And then I connect the dots. Now, again, normally this line would have arrows at both ends, but it doesn't go any further to the left because I wasn't allowed to plug in anything less than 1. And it turns out we got an absolute value graph, but that's not the issue. This is our particular piecewise function. So this is how you handle piecewise functions. Let's do another one. So first I'm supposed to evaluate f of negative 2, and then I'm supposed to evaluate f of 2, and then I'm supposed to evaluate f of 0. Now when I plug in negative 2, first of all, don't plug it into both pieces because that's not right. You're supposed to use this information on the right to decide which one to plug it into. Now, is negative 2 less than or equal to 0, or is negative 2 greater than 0? Well, it's not the second one, right? It's negative 2 is less than or equal to 0. So this is the situation we want to use. We want to plug negative 2 into the top piece. So it's 2 times negative 2 minus 1, which is going to give me negative 4 minus 1, which is negative 5. Now let's evaluate again. Okay, so this time I'm evaluating f of 2. So I'll look to see, do I use the top one? Is 2 less than or equal to 0? Nope. Is 2 greater than 0? Aha, it is. So I want to use the second piece. So I'm going to plug 2 in for the x. That's 2 squared equals 4. And then finally, 0. Erase all my scratch work up here. 0. Is 0 less than or equal to 0? It is, right? 0 is definitely not greater than 0. So it's the top piece that I use. So I plug 0 into that top piece. That's 2 times 0 minus 1, which gives me negative 1. And part A is done. All right, so just like our last problem, to graph, you want to do 2 separate t-tables. Okay? And this is, honestly, this is the easiest way to handle this. So your first t-table, you'll have x in a column, and then you'll have y equals 2x minus 1 in a column. And then you'll have x, and then y equals x squared. Like it's 2 separate problems. But you cannot pick any x you want to plug in. You want to use x is less than or equal to 0 in the first column. So give me numbers that are less than or equal to 0. Well, how about negative 2, negative 1, 0. Can I use 0? Yeah, it says less than or equal to. So I'm going to fill in that circle because the graph is going to go right up into that point and stop. And let's just plug it in. So 2 times negative 2 minus 1, that's going to give me negative 5, right? 2 times negative 1 minus 1 is negative 3. And then 2 times 0 minus 1 is negative 1. Remember, you multiply before you subtract. So 2 times negative 2 is negative 4, subtract 1 is negative 5. 2 times negative 1 is negative 2, minus 1 is negative 3, and then, of course, 2 times 0 is 0, minus 1 is negative 1. Go ahead and get that over with. Plot those points. So I'm going to graph that part in green. I meant to do the work in green so it would all match, and I forgot. So negative 2, negative 5. That's right down here. Next point, negative 1, negative 3. And then the filled-in circle, 0, negative 1. There we go. Now, that is a straight line, right? Because they're both the x is to the first power. And it's in function form, so we know the y is to the first power. There you go. So there is no arrow over here because the graph literally stops at 0. But there is an arrow on that end. Okay, now let's do the other part in red just so you can notice the difference. So I'm only supposed to use x bigger than 0, but I'm going to use 0. Why? Because I need to know where the open circle goes. So it's either a closed circle or an open circle at these points. You have to plug in whatever number that is into both equations. One's going to be open and one's going to be closed. And if it's like the last problem, one fills in the other one. Maybe not so the case in this problem though. So 0 and then other numbers bigger than 0 might be 1, 2, 3 if you want to go that far with it. Alright, so I'm plugged 0 into the x value. So 0 squared of course is 0. 1 squared is 1, and 2 squared is 4. So 0, 0, right here with a filled-in circle, 1, 1, and 2, 4. And that is the right half of a parabola. It keeps going up forever. Remember, where parabola looks like a U shape, but we don't get the left side of the U. And I messed up on my graph. You might have noticed I should have put an open circle, and I didn't. So let me go back and make a big deal about that. There we go. There's my open circle, and there's your piecewise functions. All right, number 15, are these functions even, odd, or neither? Now, to determine if a function is even, odd, or neither, there's just one step. These are different than the symmetry test. We have some of those coming up. But what you do is you substitute in f of x, or f of negative x, I'm sorry, for your x, and simplify. If you get the original function back, then it's even. If you get the opposite function back, it's odd, and if you get a mixture, then it's neither. So again, so it's even if that gives you back the original. It's odd, think opposite. That gives you back the opposite signs. And neither, it doesn't give you either one of those. Okay, I think that's pretty obvious. But this is what you have to do. You have to plug in f of negative x. So let's do this on A. So that's going to be negative x to the 4th minus negative x squared. And then you simplify. So negative x to the 4th power. When you raise a negative to the 4th power, think about it. Negative times negative times negative times negative. That turns positive. So that's equivalent to saying positive x to the 4th. Minus, and then you have to do this part. What is this? Now these two negatives don't cancel. You have to do exponents before you multiply. So what is negative x times negative x? Well, that is positive x squared. So this minus just comes down. And again, when you raise a negative to an even power, the negative goes away. Now look, that matches the original. Now what does that mean? That means that the first function, f of x, is an even function. Okay, let's change colors and do this again. So green, for example, B. Okay, it's called G. So I'm going to calculate G of negative x. So I have negative x to the 3rd minus 2 times negative x plus 1. Now, when I simplify a negative to the 3rd, it stays negative. So that's equivalent to saying negative x to the 3rd without the parentheses. Now, negative 2 times negative x, this is not raised to a power, it's just a 1, so I'm ready to multiply these together. That gives me plus 2x, and the plus 1 just carries along. Now, notice the signs. Compared to the original g of x function, this negative x to the 3rd changed from positive. This positive 2x changed from negative, but the positive 1 is still positive 1. So this is a neither problem. It does not match the original, and it is not completely opposite of the original either. All right, let's try example C. Now, I'm going to calculate h of negative x. So that's negative x to the 5th plus 2 times negative x. When I simplify that, that gives me negative x to the 5th without parentheses. Why? Because when I raise a negative to an odd power, then it's a negative value. So I write that without the parentheses. That means I simplified the negative to the 5th. Plus 2 times negative x is negative 2x. Now notice that is the opposite of the original function. All the signs are opposite. Plus x to the 5th is now negative down here. Plus 2x is now negative, which means we have an odd function. Now even functions are symmetric about the y-axis. So this x to the 4th minus x squared has symmetry that looks like that. Now, I'm not saying it looks just like that, but it is a reflection through y equals x. Odd function, neither function doesn't have symmetry. An odd function, on the other hand, the last one, has symmetry about the y-axis. So this graph that we did right here might look similar to that. has origin symmetry. I don't know if I said that or not a minute ago. Anyway, it has origin symmetry, and so it's not symmetric about a particular axis. We rotate from the first quadrant over here to the third quadrant, and you see if we rotated, this would land on top of it, or you can do two things. You can fold down the y-axis and then fold across the x-axis, and you would see the graphs land on top of each other. Now for problem 16, this is similar to even and odd. I'm supposed to use symmetry tests to determine if the equation is symmetric with the y-axis, the x-axis, the origin, more than one of these, or neither of these. Now here's the drill here. There's three types of symmetry. So there's a test for y-axis symmetry, there's a test for x-axis, and a test for origin symmetry. So y-axis symmetry, what you do is you plug in negative x for x. Okay, and this is the first one, the y-axis symmetry. And so that's going to be 4 times negative x squared plus 9y squared. I'm not messing with the y, equals 1. And then you simplify it. 4x squared plus 9y squared equals 1. It passes the test if it matches the original. And notice it does. So it has y-axis symmetry. Let me say it that way. Okay? Now let's try the next one, x-axis symmetry. To do x-axis symmetry, you plug in negative y for y. Notice it's the opposite one you plug in. So it's 4x squared, I'm not touching the x, plus 9 times negative y squared equals 1. When I simplify, that's 4x squared. Well, when you square a negative, it turns positive, plus 9y squared equals 1. Look, it matches the original again. When you do these symmetry tests, if it matches the original, it has that particular symmetry. And then finally, you check origin symmetry. And origin symmetry, you check both of them. So for origin, you do negative x for x and negative y for y. You do both. So look, if it's got both of these, it's going to have it, but I'm going to show you anyway. That's 4 times negative x squared plus 9 times negative y squared equals 1. Negative x times negative x is positive, so that's 4x squared. Negative y times negative y is positive, so plus 9y squared equals to 1. Again, it matches the original. Aha! So it does have origin symmetry. So it has more than one of these. It has y-axis, x-axis, and origin symmetry, which means it can't have neither because it has all three. All right, you ready to try this again? So we're going to try, you got to do all three tests. So the first one, the y-axis symmetry, you've got to plug in negative x for x. Okay, and again, this is the y-axis. You may want to write it down every time you do it too. So that's going to be y equals negative x squared minus 5. Look, when you simplify that, that's y equals x squared minus 5. What do you think? It matches the original. What does that mean? It has y-axis symmetry. But that you can't stop there. You got to keep checking. For x-axis symmetry, remember what you do? You plug in negative y for y. So is negative y equal to x squared minus 5? Does that match the original? Well, no. Even if you divided both sides by a negative 1 to get rid of that negative, it still doesn't match the original. So nope. All right. Now, if you don't have x-axis and y-axis, well, no, let's keep going. You could have origin symmetry, so we need to check this one. Negative x for x and negative y for y. This is called origin symmetry. So you do negative y is equal to negative x squared minus 5. When I simplify that, that's positive x squared minus 5. Even if I divided everything by negative 1, that's going to give me y is equal to negative x squared plus 5. It doesn't match, right? So that's a nope. It's not going to work. So this one only has y-axis symmetry. I was going to change colors for you on that last one, and I didn't. So let's do this. So again, symmetry. Again, I got quite a few of these just to make sure you have plenty of examples. So does this have y-axis symmetry? Remind me, what do? I plug in negative x for x. So I have negative x is equal to y squared minus 5. Okay, does that match the original? Nope. It's a negative x and a y squared minus 5 still on the other side. So no, this does not have y-axis symmetry. What do you do for x-axis? You do the opposite. You plug in negative y for y. You leave the x alone. So x is equal to negative y squared minus 5. Will that simplify? Yes, it will. X is equal to y squared minus 5, because when you square a negative, it turns positive. Does that match the original? Yes, it does. That's exactly the original. So this has x-axis symmetry. I didn't change colors again. Let me change the last one. Okay, so origin symmetry. Remember, to check origin symmetry, you do both. You do negative x for x and negative y for y. You simplify. That gives me negative x on the left and positive y squared minus 5 on the right. Does that match? No, it doesn't. Even if we divided both sides by that negative, it's still not going to give us what we have to start with. So the only thing we have this time is x-axis symmetry. By now you probably have it down, but let's see what we can do with this problem. So again, to check y-axis symmetry, you let negative x for every x. So I have y is equal to negative x to the third minus 2 times negative x. Then I simplify. Y is equal to negative x to the third. When I cube a negative, it's still negative, plus 2x. Does that match the original? Well, definitely not, right? My signs are all wrong, so this does not have y-axis symmetry. We check x-axis symmetry by plugging in negative y for every y. So I have negative y is equal to x to the third minus 2x. Does this equation match the original equation? No. And if I multiplied everything by negative 1, it still wouldn't match. So this is a no match, which means no symmetry, right? I should have put no match here. Made it look like it matches. It's not a match, all right? And then the last one is it have origin symmetry. To check origin symmetry, we do negative x for x and negative y for y. So I have negative y is equal to negative x to the third minus 2 times negative x. That gives me negative y is equal to, now negative x to the third is negative x to the third without parentheses. Negative 2 times x is negative 2x. Now that doesn't look the same as the original, but what if I multiplied this entire equation by negative 1? Can we do that? Yeah, you can. You can multiply both sides of any equation by the same value. So on the left, negative 1 times negative y is y, and on the right, negative 1 times negative x to the third is positive x to the third, and negative 1 times negative 2x is plus 2x. Look, that matches the original. No, it doesn't. Oh, that's a plus right here. That's a plus 2x inside there. I had an error. And then when I multiply by negative 1, that makes that a minus 2x. Yes, now it matches the original. I almost messed up there. So this has origin symmetry. Last one, y'all. Finally, last symmetry problem. I just had to make sure you practice this plenty of times. So the use the symmetry test. Remember, y-axis symmetry. Remind me, what do? I plug in negative x to every x, and then I simplify, and I see if I get the original function. So y is equal to, that's negative x minus 1 squared plus 2. Now, can I simplify that? Well, you may struggle to be able to compare. Like, the question really is x minus 1 squared the same as negative x minus 1 squared? Honestly, you might not know. You might not have enough experience. You could multiply it out. Y'all know x minus 1 squared is x minus 1 times x minus 1. That's x squared minus 2x plus 1 when you FOIL it out and add like terms. Whereas this one, negative x minus 1 times negative x minus 1 is x squared plus 1x plus 1x plus 1. That's going to give you a plus 2x. So this is not the same as the original. So you had to do a little bit of work there to compare. This is a tricky one. I threw this in at the end just for you to think about. But these don't match. But it's hard to tell the way it is. So again, I multiplied that out. And I multiplied that out to see if they were the same. Because the plus 2 at the end is definitely the same. But they are not the same. One is minus 2x in the middle. The other one's plus 2x. So this does not have y-axis symmetry. Okay? Does it have x-axis symmetry? Remember, to check x-axis symmetry, we substitute in negative y for y. So that's negative y is equal to x minus 1 squared plus 2. Now, even if I got rid of this negative, because it's not here originally, and multiply the other side by a negative, that would put a negative in front of that square and make that positive 2 negative, and it wouldn't match. So either way you go with it, that one doesn't match the original, therefore it doesn't have x-axis symmetry. And then the last one is, does it have origin symmetry? And we have seen a problem that had origin symmetry, but it didn't have x or y symmetry, so that can happen. That's negative y is equal to negative x minus 1 squared plus 2. Okay, now again, remember we had trouble comparing. We know that this on the right is definitely not equal to that. But what about this negative in front? Like if I multiplied both sides, like if I multiply the negative to the other side, that would give me negative x minus 1 squared plus 2. But then if I multiply that out, that's going to make this a negative x squared. And it's still not going to match, y'all. So if you multiply them all out, you're going to realize that they don't match. Okay? You might be struggling with that one a little bit more, but I don't want to take too much time getting bogged down in this one. Again, if you FOIL all that out, there's no way that's going to match the original. And if you FOIL that out, it wouldn't either. Okay? All right, we have some good stuff right here. So for the following graphs, identify the basic function. Remember, I call that the toolkit function, the parrot function, the common function, elementary functions. Gosh, there's so many names for it. I just want to know what that basic shape graph is. And the basic function over there to the left, that is an x squared. So I want you to write it as f of x equals x squared. And then I asked to describe the transformation. Now notice, f of x equals x squared looks pretty much like that. Okay? Except better. Now, how have we moved this one? Okay, well, look, we've moved it to the right 2 and up 3, right? Every single point is moved to the right 2 and up 3. So that's what I write, right 2 and then up 3. Now, we know right 2 is a horizontal shift, right 2. Up 3 is a vertical shift, up 3. There's no reflection because it's not flipped upside down. And now we're supposed to find an equation. So call it something like g of x if you want to. Now, if you move left and right, remember, that means you add or subtract to the x value. So that's going to be x. Right was minus 2. And then the square part goes on the outside. The up 3 goes outside the function value, so plus 3. So that's what we're looking at for the equation right here. Next problem, what's the basic graph? So you need to recognize that that's a square root. So the basic function is f of x is equal to square root of x. Now the question is, what have I done to the square root? Now the basic square root kind of looks like that right there. Okay, an arc over. Notice we moved it once again to the right. We haven't moved it up, but we moved it to the right 3 units. So we move this thing to the right 3, and that looks like it. It's not flipped around the wrong way or anything like that. Just move to the right, no reflections. And I also commented here that there's no stretch or compressions because those are too hard to look at a graph and determine. I say they're not too hard. It's just something we're not doing. It can be done. Okay, but we moved right 3. So we remember when you move left and right, you add to the x value. So I've got to do something to this x value. Right was minus, so this is going to be, and let's don't call it f of x again. I wouldn't count off if you did, but let's call it g of x. So g of x is going to be the square root of x plus 3, because we moved it to, minus 3, because we moved it to the right 3. How's that? Let's keep going. What do you think this graph is? Basic graph, f of x, how about equals square root of x, right? It's that arc over, but it looks crazy. It looks like maybe it's upside down, because normally square root has kind of that shape right there, right? Well, it looks like it's been reflected, and when it's reflected upside down or through the x-axis, it would look like that, right? So, and then we just moved it up. So it's a reflection in the x-axis. And it's also moved up. I didn't have to write the word moved, but moved up. How many units? Well, how about 1, 2, 3? Oh, no, that's a 2 up there. Let me pay attention. Notice that's a 2. So there's your 1 right there. There's 2, there's 3, and then, of course, you see 4. So pay attention to your scale, but we've only moved it up 2. Now, how am I going to write that? Well, remember when you move up or down, you add that outside the function. When you move left or right, you add that to the x value, but we didn't move left or right, but we reflected it in the x-axis. Do you remember where the negative goes when you do that? It goes in front of the function. So you have g of x equals negative square root of x plus 2. Okay, I got 2 more of these before I call this video done, and then we'll do another video for the remainder of the material. So for the following graphs, identify the basic function, describe the transformation, and there are no vertical or horizontal shifts or compression. So what's this basic guy? Well, that's an absolute value, right? So f of x is equal to the absolute value of x. That is the basic function. Elementary function, parent function, toolkit function, common function. I'm sure there's more names, but there you go. There's your basic function. Now, what have we done? Well, it's upside down. So we have reflected it, and we have reflected it in the x-axis. So you got to tell me which axis it's reflected in. Okay. What else? I think I moved everything to the right, didn't I? I sure didn't mean to. I'm sorry. So to the right 1. So we have moved to the right 1 unit. We haven't moved it up or down because the vertex, the pointy part, is still on the x-axis. Now, when it's upside down, or reflection in the x-axis, remember the negative goes in front of the function. So when I write this equation, or function, it's going to be negative absolute value of x like that. But since I moved it right, I have to do minus 1, and then I didn't move it up or down, so I don't put anything outside. And there we go. And again, I apologize to you. I moved everything to the right and not the left. But had this been moved over to the left, say it was like that, that would be absolute value with the negative in front, just like we did, and that would be x plus 2. See what I mean? And you call it something like g of x. All right, so there's a left one. One more of these, I'm calling it. Okay, you recognize this basic shape? So this basic shape is f of x equals x to the third. And the basic x to the third looks similar to that right there. And so we're pointing in the same direction. We haven't reflected it at all, but we've moved it down. Notice that this part that's usually right here at the origin has been moved down 4. So when we write the new equation, it's going to be x to the third minus 4.